Good morning. I am Professor N.V.S.N. Sharma from NIT Warangal. I am going to teach the subject on radar engineering. Before we go into the details, let us just look at a common situation. All of you must be watching cricket these days. In that, when the ball is released, immediately you are getting the speed of the ball on the screen. Have you ever thought of how is it possible? Is somebody going to measure the time and the distance covered, taking the quotient? Is he getting that velocity? Or what type of instrument he is using to get this? Please understand that it is done by a system called radar. This instrument will have a transmitter and a receiver to process the signals and display the velocity. A radar is an electronic device like your mobile which can measure velocity, distance, and also the angular coordinates of different types of targets. The targets can be aircrafts, ships, missiles, human beings, cycles, or cars, any other moving objects. Here, the word radar is coined from the operation the instrument can do. That is, we transmit electromagnetic waves towards the target. As the object is having metallic content, it's going to scatter the electromagnetic waves incident on it. A small portion of it will be traveling in the reverse path and reach the receiver. The receiver will receive this echo and process it to display different parameters like velocity, distance, angles, or similar parameters. So, the radar is a measuring device, though it uses many of the principles used in communication engineering, but the main job is to measure certain parameters. Now, let us see how this word has come, what are the frequencies we use, what are the applications, what are the types we have, and similar details. A radar is to get the distance indication and also to get an indication of the target first. So, the similar word for electromagnetic waves is radio waves. So, here we say that radio detection is done first and then ranging. That means measurement of distance. So, all the first letters of these words, radio detection and ranging, have been put together and made it as a word called radar for the system which does this job. So, here we are going to have a transmitter and an antenna to radiate the electromagnetic waves. Usually it will be a pulse. The pulse is transmitted first and your counter will start. So, as the pulse travels through the atmosphere and reaches the target, it gets scattered. The reverse of this is going to take place from then on, and you will receive the echo at the receiver point. The time taken will be counted and the velocity of the wave in the free space. If you take the product, you will get twice the distance, as the signal has traveled as 2 times the distance. So, the time taken into velocity divided by 2 gives you the range. In this, we have different terms, that is the target range, target angles, target size, speed, and other features that will modify the final results to a certain extent. The data that is processed will be displayed on a scope as shown. So from this we can get the information on the distance, that is range, the azimuth angle, that is the angle from the true north of the target, and also the elevation. The display is a normal CRT display but modified to get these indications quite easily. This is known as plan position indicator, and a radar operator will be easily identifying the direction and the distance of the incoming target as the blip will be coming up on the scope as shown. So different blips on the scope indicate different targets that are present in the surroundings. The distance measurement is in terms of nautical miles, which is 1.852 kilometers. Before we go into the details, it's worthwhile to know the history of this radar. The idea is conceived as early as 1880 by Henry Hertz. He suggested that radio waves could be reflected off metal objects, and Britain built the first ground-based early warning system called chain home in 1930s. By 1940s, a high-power microwave source could be invented called as magnetron. By using this, people were able to send signals to far-off distances and get the echoes which can be processed by a good receiver, and hence they could get the indication of the incoming targets, though the target is present at hundreds of nautical miles away. So there, by World War II, the radars became a normal measuring system for most of the military applications. And here the different roles that are played by early radars are for early warning, target acquisition, target tracking, target illumination. Moreover, they are also used for other applications like ground mapping, collision avoidance, measurement of height known as altimeter, and also for weather warning. That is, to understand the moisture content, wind velocity, etc. of the weather, and to predict what will be the weather condition in the coming 24 hours time or 1 week ahead of this. Thereby it could facilitate the air travel to a great extent. Generally, the frequencies used for these applications range between 100 megahertz to even 100 gigahertz. So in the electromagnetic spectrum, these radars are used in the frequency range of 10 power 7 hertz to 10 power 11 hertz as shown in the diagram. Within this, again, all the frequencies are not being used because they have been allocated separate jobs. So within this huge amount of range, certain frequencies are only used for radar applications. So you can see in the diagram what are those specific frequencies meant for different types of radars. And to facilitate this, exclusively for airborne radars, a separate chart is prepared which is as shown, and the corresponding numbers are also given in a tabular form like this. So in this, the nominal frequency ranges are given and also the ITU assigned values are mentioned. How come we could get these things? These frequencies are identified taking the atmospheric attenuation of the electromagnetic waves. So as you can see from the graph, the atmospheric attenuation is low only at certain frequencies, and at these frequencies we use radars for surveillance, for attack helicopters and anti-tank missiles, and also for fighters as indicated. So The frequencies are mainly decided based on the attenuation of these waves when they travel through the atmosphere. And using this data on a scope will be facilitated by printing the plan of that location as shown in the diagram. So we will be able to identify from which direction the aircraft is coming, at this time, in which city it is flying over, and by next 10 seconds or 40 seconds time, where is it going to be, and when we should be alert to eliminate that. That means within the range of the firing gun, when is it going to come and when should we attack it to eliminate entering into our territory. So this is all done using a scope called PPI very conveniently. As mentioned earlier, the range is decided based on the time elapsed for the signal from the transmitter to go to target and return to the receiver. This time into velocity of the wave in the free space, that is c, by 2 gives you the range, which is a very simple calculation. So using a single pulse we must be able to do it, but to improve the accuracy, generally we go with 3 or 4 pulses or even more and get a very accurate data of this range. Mind you, why do we use this divided by 2? The 2 is because the measured time is for 2 trips, that is from the transmitter to the target and from the target to the receiver. The total time is taken into account, and hence the range is calculated by this equation. So how exactly it is happening is diagrammatically shown now. So here a transmitted pulse is going first from the transmitter towards the target. The target is going to scatter all this. A small portion is reflected towards the receiver placed next to the transmitter, and the reflected pulse will be processed in the receiver and we get the required parameters of interest. Here in the radar, the direction of the target is also another important parameter. So this is also measured from the antenna location, which is used along with the transmitter and receiver. So this is very much useful in the situations like air traffic control. The strength of the received signal must be such that the process can be easily done and the noise is removed as much as possible, and the strength of the signal is dependent on the distance and also the shape of the target. From these things we can identify what are the types and uses of radars. Such radars scan a large area with pulses of short radio waves. These are generally to first identify whether there are any incoming targets before the radar system. Once a target is identified, then a tracking radar will take the data of this incoming target on a continuous basis and project it as the trajectory of this target for easy cancellation using a firing gun. So such radars are for identification first, and then the tracking radars will be used to continuously track the incoming target and see that it is eliminated successfully. Navigational radars are like such radars, but they use short waves that are reflected off hard surfaces. These radars are used on commercial ships and for long distance commercial aircrafts for many applications. Then we also have radars specially meant for mapping of the ground. They are known as mapping radars, meant for remote sensing and for geography applications. Nowadays we are finding wearable radars which will be used as a substitute for the eye. Then we have air traffic control, which uses a radar to reflect echoes of an aircraft. Then a separate class of radars are there known as weather radars to understand the behavior of the atmospheric particles, moisture content, wind velocity, etc. to understand the incoming rains, storms, cyclones, etc. Weather radars use radio waves with horizontal, dual or circular polarization. And some weather radars use Doppler effect to measure the wind speeds. Incoherent scatter radar, that is another radar application. It is used to study the Earth's ionosphere and its interactions with upper atmosphere, the magnetosphere and the solar wind. With all this information, now we are ready to go into the basics of these radar systems. So let us see first what are the basic types. With all this information, now we are ready to go into the basics of these radar systems. So let us see first what are the basic types. There are basically two basic types of radars. One is a continuous wave radar and the other is a pulse radar. By the name of it, you can understand that in one system we are going to send continuous waves like sinusoidal waves, etc., and receive them to get the required data. Whereas in the second case, we are going to transmit pulses of energy, and during the intervening time between two pulses, we are going to receive the signal and process it. These two types have their own advantages and limitations. So let us see first what is a continuous wave radar, how does it operate, what are the advantages we have and what are their limitations. By the name itself, we understand that it employs continuous radar signals. So there will be separate antennas for transmission and reception. And the basic principle of operation depends on Doppler shift. So first let us understand what is this Doppler shift is. This is dependent on Doppler phenomenon. What is that Doppler is? It means when a source is radiating and a receiver is receiving these signals, there will be one frequency of operation for this. But if either the source or the receiver is moving, then the received signal will have slightly different frequency. The shift in this frequency is known as Doppler shift. Shift can be positive or negative frequency depending on whether the movement is close to each other or away from each other. So whenever there is a relative velocity between source and the receiver, there is going to be a change in the received signal frequency, and this is the fundamental principle on which the CW radars are developed. From the diagram, you can see that when the target is moving away, the received signal frequency will be reduced. When the target or the receiver is moving towards the source, then the received signal frequency will be higher. So with all this, you can see what is a block diagram of a continuous wave radar. In this, a continuous wave source, an oscillator, is used to radiate the signals first. So the signal is radiated by an antenna, and the signal goes to the target, gets reflected and comes to the receiver. At the first stage of the receiver, there is going to be a mixer which will take out only the Doppler shift. So for this purpose, we use a sample of the transmitter signal along with the received signal. The difference between these two will be the output of this mixer. This difference frequency or beat frequency will be amplified, and the beat frequency contains the information on the velocity of the target. So using a discriminator, we will be converting this Doppler frequency into equivalent voltage, and that will be displayed on an indicator like this. So here the velocity of the target can be easily displayed to a high accuracy. As you can see, the block diagram is very simple, and hence the system is very inexpensive, and the power requirement for this is also generally very low, and the amplifier, the discriminator are very simple circuits in this context, which are used normally in FM transmission systems. Now let us see what is a pulsed system. Pulsed radar is characterized by a high power transmitter that generates an endless sequence of pulses. The rate at which the pulses are repeated is defined as pulse repetition frequency. In this, there are other parameters like what's the pulse width, which is usually expressed in microseconds, the pulse repetition frequency, which is normally kilohertz, and the pulse period, which is the reciprocal of pulse repetition frequency, hence it will be in microseconds. As you can see from the diagram, the pulse is kept on a carrier of very high frequency, which is known as the radar carrier frequency. And from the diagram you can also see what is that pulse repetition time and the resting time. So when the pulse is transmitted, the transmitter is switched off and the receiver is made on. So the pulse goes up to the target, gets scattered, returns to the receiver. Now the receiver is going to receive this, then the receiver will be off, again the transmitter will be made on to radiate the second pulse. Like this, at any given time the antenna will be connected only to transmitter or to the receiver. Pulse width plays a very important role, so whether it should be long or very short is a point of discussion in the design. Similarly, the pulse repetition time is another important parameter, and the reciprocal of this is pulse repetition frequency. That will also be having a bearing on the results what we get. Pulse width can determine the radar's minimum detection range and also what is the maximum detection range. The PRF can determine the radar's maximum detection range. That means how far the target can be so that it is properly detected by your radar system. Similarly, how close the target is so that it is still detected by the radar is the minimum. Why the radar is not able to detect is that when the transmitter is ready to send the pulse, the receiver is not connected at all, and hence the signal that is reflected from a close by target will not be received by the receiver. That can be considered as a drawback of this system, but there are several other advantages by which we prefer to go with the pulsed systems. So now we can discuss on the parameter pulse repetition frequency, and when we vary this, what are the effects we are going to have. Another parameter of interest will be peak power, that is maximum signal power of any pulse, and how does it affect the maximum range of radar. And we are going to develop a relationship of average power to pulse width and pulse repetition time. Now let us discuss on the effect of increasing the width of the transmitter pulse. Suppose you are having a long width of pulse. At the start of the pulse, the antenna starts radiating, and if the target is very close by, it reflects the energy, but as the antenna is still connected to the transmitter radiating the long pulse, the reflection will be lost, and hence you can see that there is a dead zone before the transmitter. What we mean is that within this dead zone the target cannot be detected. So long width of the pulse is not an advantageous one when you are handling targets which are very, very close by. To understand these things better, we have an equation as shown. That is, the maximum range is decided on pulse width and pulse repetition frequency. From this equation, you can see if the pulse width is increased, the minimum range that can be detected gets reduced, but as the energy contained is more, you can get good echoes from very far off targets, resulting in high range possible, or the maximum range that can be detected will be very high. On the other hand, if you increase the pulse repetition frequency, as the pulses are packed close by, you will not have sufficient time between two pulses to receive the signals from far off targets, and hence the maximum range gets reduced. So pulse repetition frequency and pulse width have a direct bearing on maximum range that can be handled by a radar system. With all this information, let us now see what are the blocks required for a pulse radar system. One is a synchronizer, a transmitter, an antenna, a duplexer, a receiver, display unit, and for all these things to work properly, we need a power supply. In all these blocks, we have some basic knowledge on synchronizer, transmitter, antenna, receiver, display unit, etc. But the fourth one, that's a duplexer, which is a special component used only in radar systems. This duplexer will facilitate the job of the antenna. As we understood before, the antenna is connected to the transmitter for some part of the cycle, and then it is connected to the receiver for the later part of it. To do this job efficiently, we need this device called duplexer. This is like a traffic policeman. When the transmitter is giving the signal, the antenna is connected to it through the duplexer, and when the antenna is receiving the signal, that will be passed on to the receiver by the system. So a duplexer is an additional component required to see that one antenna can be used in this. Otherwise, we need to go for two separate antennas, and handling them will be more difficult. All these blocks are interconnected as shown in the diagram. So a power supply is going to give the required power to all these blocks. The synchronizer will send a start signal to the transmitter. Then the transmitter is going to give a pulse which is sent to the antenna through this switching unit called duplexer. So here the job is done by ATR switch, anti-transmit receive operation. system of the duplexer is known as ATR switch. So using this, we are able to send the transmitter signal only to the antenna but not to the receiver. So the antenna is going to radiate this, and a sample of that will be sent to the receiver unit for synchronization purposes. When the received signal is present, the antenna is now connected to the receiver through a TR switch, transmit receive portion of the duplexer, and the received signal will be very much small compared to the transmitter signal. So to protect the receiver from a high input from the transmitter, this duplexer is a must, and people say the duplexer must be able to provide a high amount of isolation between transmitter and receiver. So if there is any failure of this duplexer during the operation, the receiver is going to be the most affected one. Mind you, the transmitter signal will be in the range of watts, hundreds of watts, or even in kilowatts, whereas the received signal from very far off targets, which are hundreds of nautical miles away, will be in the range of 10 power minus 25, minus 26, or even minus 28 watts. So the isolation required between transmitter and receiver will be 10 power 3 to 10 power minus 28. So of the order of 10 power minus 30 watts of isolation is required between these two things. That is the importance attached to this device duplexer. Now coming to the receiver is going to process the signal only to see that the high accuracy is maintained. The signal shape can be distorted, the noise can be removed in many ways, but whatever we do, it is only to see that the accuracy of the measurement is improved. The processed signal is given to the display unit through this video part of it. This is also synchronized with the transmitter signal, and there are varieties of displays for different applications. We have the names like A scope, B scope, C scope, and PPI of these types. We shall see these details at a later stage. This is the architecture of this pulse radar system. So here the synchronizer is going to send the signal to the modulator. That means the pulse is kept on the microwave signal. So the signal that is coming out will be amplitude modulated, and this will be amplified to the required level in the transmitter, and this duplexer is going to again see that the antenna is properly connected to the transmitter at the time of transmission. So for this antenna to be able to send the signal to different directions, we have a servo motor mechanism, and there is going to be a compass attached to this to indicate the direction of transmission and hence the direction of arrival of the target. The received signal is sent to the receiver through a protecting device. This protecting device is like a fuse. If by any chance the duplexer fails, the transmitter signal can be directly sent to the receiver. At that point of time, when the signal going through is beyond a particular limit, this fuse will be blown off and the receiver is protected from this high power. So it is basically a protecting device to see that beyond a particular power level, the signal doesn't go into the receiver. So this receiver is going to remove the carrier first, process the received echo further, and this will be processed in amplitude as well as in phase so that we get much better detail in the display. For all these things, there are good control system that will be required, and all this different blocks are supplied the power through a special power supply unit. So for a lab-based system, you can see more and more details of these blocks. So there will be an RF oscillator, that means a sinusoidal high frequency generator, and a separate pulse generator for these things, and both of them will be sent into a modulator device. So we can see that external modulation scheme is normally employed in these things, and this is given to a rotating antenna pedestal so that the antenna can send the signal to different directions. So the antenna is sending these things to different target locations, and the received signal is now sent to the receiver for the processing. So this is the radar receiver we have, and in this the dual channel sampler to get the amplitude and phase informations of the received signal by comparing it with the transmitter signal. And then we are going to have high power signal processing techniques. In this context we call them as radar signal processing techniques, and the resultant data is now displayed on an oscilloscope like this. Why we use pulses is to see that a high amount of power is sent within a short duration, and in this the terminology used is pulses. How many we are sending per unit time we take into account, and we call this as pulse period, and the pulse is on for a certain duration which is known as pulse width. If you take the Fourier transform of this, it's going to be as seen like this. So in this we have the bandwidth of the pulse required and the center frequency of this. So the pulse period, the inverse if you take, we are going to get the center frequency of this, and the pulse width will have the information regarding the bandwidth of this sinc function. So in the frequency domain, the transmitted and received signals are composed of spectral components centered on the radar operating frequency. The practical limits of the frequency response will be f0 plus or minus 1 by tau, and hence the receiver should have a bandwidth of 2 by tau, that is a minimum bandwidth required. It is better to have definitely more than this in practical cases. Now let us spend a bit of time on pulsed radar average power. So since a pulsed radar only transmit for a small portion of the time, so the average power is given by the peak power into pulse duration divided by the total pulse width. We'll take a simple example, that is a pulsed radar with a 1 microsecond pulse width and a medium PRF of the order of 4 kilowatts transmits a peak power of 10 kilowatts. In such a case, what is the average power of this? So the peak power is 10 kilowatts and the pulse width is 1 microseconds. So divided by the PRT. But in this context we got PRF as the data. So putting that into the equation, we get this so much watts. But normally we express these in terms of dB over watts or in terms of dBW. Now we may get a doubt that suppose two targets are coming one next to each other, how do we distinguish? Yes, we can distinguish two successive radar targets by a term called pulsed radar range resolution. This signifies its ability to distinguish two closely spaced targets along the same line of sight, and this is a function of the pulse length, and the relationship is as shown. So if two targets are close by, they can be identified as two separate targets if the pulse length is less than the difference of the distances between the two targets, twice of it. 2 times R2 minus R1 must be greater than this pulse length. Here you can see a pictorial view of this range resolution. So if a transmitted pulse is going, then it hits the first target and starts retracing. Then the transmitted pulse is going to hit the second target and starts retracing the path. So the two echoes are spaced again in a similar manner, and we should be able to receive both of them successively before the start of the next pulse. So for this we have the equation as shown in this. The LP must be less than or equal to 2 times R2 minus R1. So this is the complete picture of this range resolution case. Then we also have a problem of range ambiguity. The PRF is another key radar parameter, and it is very difficult to design. That means how to take a decision on this is very tough. The range of a target becomes ambiguous as a function of half the pulse period. So targets that are further than half the pulse period yield ambiguous results. So R ambiguous is C by 2 times PRF or CTP by 2. So this diagram clearly indicates the radar range ambiguity that is likely to be there. From this diagram we shall try to understand what we mean by range ambiguity. Suppose when the aircraft is crossing the radar system, we transmit a pulse. As the aircraft goes to a certain distance, we get back the echo within the next pulse time. But if it goes beyond a particular point, then also we are likely to get the echo before the start of the next pulse. But if the PRF is too high, then there is every chance that the pulse echo of the distant object returns after the second pulse is transmitted, as shown in the second picture here. So the echo corresponds to the first pulse, but it returned to the radar after the second pulse is transmitted. So the radar operator will have a doubt whether this echo corresponds to the first pulse or second pulse. This is what we call as range ambiguity. There is an ambiguity for the operator to decide on the range of this target, whether this range must be identified as this time interval multiplied by velocity divided by 2 or this time interval multiplied by velocity divided by 2. So this is a very great problem, and this sort of echoes when we receive, we call them as time around echoes. And this graph indicates what is the period of different distances we get corresponding to the PRF what we choose. Effect of pulse period on target ambiguity is shown in a graph like this. So if you increase the PRF, the ambiguity is also going to increase. A very nice picture is shown here to understand these things in a better manner. So here you can see the return time of first target, the return time of the second target. So these are all within the ambiguous point of this. But suppose the echo comes after this time, there is a very good chance that we'll get into the ambiguity of this radar range. So thereby a target whose range is within 2 times PRF of this, then we have an ambiguity on this. In this diagram we are going to show you how a radar operator will get into some ambiguity. Suppose the pulse is returned after half the time of pulse repetition time, then you can see that it is likely to get into the problems like this, because for the next one it's going to come after the second pulse is transmitted and the return time is very long. So the operator will have a confusion whether this echo corresponds to the first pulse or the second pulse. So thereby we should see that the echo returns definitely before the next pulse is transmitted. So this is a very clear example of the range ambiguity for a distant target like this. So once the target comes close by, the ambiguity will be removed because the echo will definitely return before the onset of second pulse. If you are having a broad beam for the transmitting antenna, the two targets will be sending the echoes which will fall within the 3 dB beam width of the antenna, and the antenna will give equal gain for both of them, and at the receiver you will not be able to distinguish whether the target is at this position or at this position. You will feel that there is only one target present. But if you choose the beam width to be very narrow, you can definitely identify that there is one target. After that there is a blank. Then when the next beam is placed on this, you can identify that there is another target. So for these two targets, you will get two separate indications very clearly on the receiving system, and there will not be any ambiguity for the operator to understand that there are two separate targets for this. So choosing the beam width of the antennas is very crucial in the angle resolution aspect. With all this, let us now try to compare the two types of radars, pulse radar and CW radar. So in a pulse radar case, as we have seen earlier, we can get away with a single antenna system, whereas in a continuous wave radar you require one for transmitter and another one for the receiver. So two separate antennas will be a must. The pulse radar gives range information, usually altitude also. This also can give range as well as altitude, and this requires a high SNR. But one major problem we find with pulse radars is that it is susceptible to jamming, whereas a CW radar is more difficult to jam, but it can be easily deceived. The physical range determined by pulse width and PRF, and amplifier can be tuned to look for expected frequency for these things. That means here there is nothing like a pulse width, pulse repetition frequency, all those things deciding everything in the case of CW radar systems. Now let us see what are the types of modulations we employ. Here normally we go with the amplitude modulation of the sine wave, but in the case of CW radars you need to go for frequency modulation to get the range information. So FM CW radars are used to get the range, otherwise it is not possible also. Then for the pulse radars normally we go with pulse amplitude modulation, wherein the amplitude of the pulses will be changed. In certain cases definitely there is a use of pulse frequency modulation. The different types of modulation schemes result in different modulated waveforms as shown in this diagram. Now let us concentrate on the antennas that will be used in the radars. What is the purpose? There are two basic purposes. One is it should radiate the RF energy, and we should also able to send the energy in the desired directions and restrict that in undesired directions. That is what we call as it should provide a good beam forming and focusing. And for normal operations, as we know from antenna theory, that the length of the antenna must be proportional to half the wavelength of operation. But this gives a very wide beam. If the wide beam is required, like in such operations, it is okay to go with these λ/2 dipoles. But we know very well that for tracking applications we need very narrow beams. The narrow beam can be obtained only with large sized antennas like parabolic antennas. So the performance of an antenna is measured in terms of its beam width, and A beamwidth has a direct bearing on the angle resolution, as we have seen earlier. So here, if two targets are approaching a ship A from close by directions, then if the beam radiated by the ship is very broad, it may not be able to distinguish. Whereas ship B is having a very narrow beam, though the targets are very close by, you will be able to still distinguish because of the use of these narrow beams. So, how do we go with the azimuth angle? The relative bearing of the ship with reference to the north is taken, and that gives the azimuth indication. In certain cases, people take the target angle, the ship looking direction, and the north to finalize this azimuth angle, as shown in the diagram. Many cases it will be required to understand what is the height of the target. So from the diagram as shown, by measuring the slant range and the angle of elevation, we will be able to fix what is the altitude of the target with reference to the antenna location. The altitude is taken from the tan of the angle of elevation and the slant range. Then how do we go with the concentration of the energy towards the target? One good technique people are employing these days is by using linear arrays. The advantage we get is that we can operate in different modes, and a linear array will have a constructive interference of all the radiators in the special directions and destructive interference in undesired directions. And the next option can be using lenses, that is basically reflectors. The diagram indicates a sample case of an array. As you know, there are two types of arrays, broadside array and endfire array. The diagram indicates a broadside array with a spacing of lambda by 2 from each element. The other variety that is possible is reflector shaped antennas. The most common one is a paraboloid antenna, which is used for conical scan, and it can be used with CW systems as well as with pulse systems. To get a broad beam in one plane and a narrow beam in another plane, we go for a modification in the paraboloid shape that is known as orange peel antenna. It is used normally with CW fire control systems. There is another option available made up of parabolic cylinder. This is for wide set beams and for long range applications. Different parabolic antennas are as shown. The main concept here is different diagrams indicate what are these different modes that are possible. This one indicates air to air search. How we do it? Similar to a raster scan, we go with the azimuth, and step by step we go with the elevation. So this is for air to air tracking of other targets. This is tracking while scanning is going on. This diagram indicates how we can go with ground mapping. So CW illumination is for some varieties of targets, and putting all these things together can also be done. That is the multimode operation, which is possible with planar arrays. Thank you.